Hi class, in this video we're going to be talking about section 3.2, addition of whole numbers. And so in our last video we were talking about number systems and the fact that numerals had different values depending on their location. Whether they were in just the ones place, the tens place, or hundreds place, right? So we had place value in addition to numeral value or quantity. And so once we have the concept of a number, of a quantity, it often makes sense to put numbers together. So a little bit of history. And is et in Latin. And et, when typed or written quickly, looks like that. And that et gives us the ampersand, which is why we have the and symbol. And it gives us the plus sign, which of course is behind my head. And so the notion of addition is of one number and another, of joining two quantities. And so when it comes to combining quantities, there are many strategies and approaches. And they're all here just so you have the names, but we're going to work through them kind of one at a time. So the first is the set model, where we have some group of objects, another group of objects, and we put them together. We have counting on, where we have some group of objects, and then we add some more to it. Number line is where we can put them on the line and add them up and go on that way. Place value operation, starting to think a little bit more sophisticatedly and thinking about regrouping ones into tens or tens into hundreds. And then once we're comfortable with that, we can work within a particular place value to find partial sums. We use what's called the left to right addition algorithm. We use compensation, where we find friendly numbers, say like 7 and 3 or 10. And so using things like that to our advantage, before finally getting to the standard algorithm. And roughly, these are roughly in order of sophistication, but also roughly in order from single to multi-digit. So the standard algorithm, where we stack two numbers above each other and put a plus sign, isn't particularly helpful when we have 1 plus 4, right? That's really where we're going to need to have 1, 2, 3, 4, 5. 1 plus 4 is 5, and that's the counting on strategy. So a set model is one way to represent the addition of whole numbers. So here we have a picture. Suppose Jane has 4 blocks in one pile. That's this pile on the left. And suppose that she has 3 in another. How many does she have altogether? Well, that's this 1, 2, 3, 4, 5, 6, 7. And so it's important to note, if this one on the left, say, had A, B, and C, and this is where we're going back to our set lesson, if this had E, F, and B, the union of A union B, in this case, would be A, B, C, E, F, which only has 5. Right, and so we need to make sure that when we use a set model, we are looking at things multiply. And I'm going to revisit this really formal notion of union in a few slides from now. But what I want you to think about is set model. We have 2 sets of objects. Count the total. And that's pretty much where we start in terms of thinking about addition. And so notice there's that set about being disjoint. They can't have any elements in common, or we might say that 4 plus 3 is 6, if, say, both of them had a D in it, right? So, generally speaking, set model, we're going to have some number of objects, 3 blocks and 4 blocks, and we're going to put them together and say we have 7 blocks. Now, counting on is slightly more sophisticated. So suppose Jane has 4 blocks in one and 3 in another. Then how many are there together? Well, so she has 4 to start, and then she has 5, 6, 7. So she counts on. So that's right, that's where this name counting on comes from. Counting on. So we have 4, 5, 6, 7. Which is different than our set model where we had 4 and 3. And we said, well, that's 1, 2, 3, 4, 5, 6, 7. Right? So set model really relies on counting. And actually, let me go back because I want you to have a word. Set model reinforces 1-to-1 correspondence, which is the idea that each item that you count corresponds to 1 in the total quantity. Right? So this A is that one, B, C, D, E, F, and G. And at this point, the slide's barely readable. But here we have to count the total quantity, whereas with counting on, we start at a number and continue. Now a number line. So it's important that students can understand that the sum of two numbers can be found by placing 2 arrows on the number line and figuring out where it ends. So for example, right, like that's lovely, those are a lot of words. Kenzo has 4 feet of red ribbon and 3 feet of white ribbon. How many feet of ribbon does he have altogether? Well, in this picture, what we see is he has the 4 feet of red ribbon and 3 feet of white, which means we have 4 plus 3 or 7 altogether. So you can see how this is similar to counting on, where we had 4, 5, 6, 7. But this is another level of abstraction because, again, we're just looking at the numerals and the values they represent and the fact that addition is their together, their and, right? 4 and 3. So 4 and 3 are 7. And then once we start moving into place value operation with addition, what we start to see is we work with really physical objects. We work with manipulatives. So this is with manipulatives. Where if I have 15 plus 7, I have 1 long and 5 units. That's 15. And 7 is 22. And the reason it's 22 is because when I look at these 10 ones, I can rebundle them into a long. So I have 1, 2 longs, but then there are these 2 ones left over. Because I have 22 left. And that, very concrete with manipulatives, is what leads us to the more generalized standard algorithm, where we start to think about place value. And I have a slightly larger example, 459 plus 193. Well, 9 plus 3 is 12, so I have 12 ones. 5 plus 9 is 14 tens, and 1 plus 4 is 5 100s. Well, I can't have 12 ones, so I need to take one of those and rebundle it. So then I have 15. But again, I can only keep the 4 here, and that 1 needs to be rebundled. And so we have 5 and 1 is 6, 4 and 1 is 5, and 2 is 2. So we have 652. And so notice this is a step that we don't often see, because if we would do 459 plus 193, traditionally we would write 9 plus 3 is 12. So we have 2 ones, and we rebundle 1 and bring it to the top. 5, 1 is 6, and 9 is 15, so we have a 5. We rebundle up top. 4 plus 1 is 5, and 1 more is 6, 652. But this is the most abstract way that we can think about addition. because behind the scenes we have place value and we have no concrete model. Right, whereas even here with our unit frame, our place value chart, what we have is a reinforcement of the fact that these are place values. But none of that is happening here. We just have to remember that we have ones, tens, and hundreds. And when we rebundle, for some reason, we stick it up top, right? Whereas here we really think about the idea of 12 ones, because we have one that gets rebundled, or 14 tens, one gets rebundled into 100, and so on. And so once we have some sort of place value understanding, once we can work with those columns, we can do what's called partial sums. And we call it partial sums because we find part of the sum by place value before finding the total. So 459 plus 193, we can look at the hundreds. 4 and 1 is 500. 50 plus 90 is 140. And 9 and 3 is 12. And so to add those up, we get 500, 640, 652. So that's 652. So we add first by the hundreds, then the tens, then the ones, and then we add across last to get our actual sum. So again, like our goal here isn't so much learning how to add, but what are our different representations for addition? What are different models and ways to show addition? Compensation is where we use friendly numbers. So here we have 48 plus 27, which is a process that would typically involve regrouping. Well, if I just take 2 from the 27 and give it to the 45, that's the same as doing 50 plus 25. And it's like, well, why can we do that? Well, think about if we have a number line, 48, 27. It doesn't matter if I instead do 50 and 25. In both cases, I'm going to end at 75. Right? And so thinking about even the number line model later leads into why the compensation model works, or the compensation algorithm. And I'm going to use algorithm and model somewhat interchangeably. They're not the same. A model is a way to show it, and an algorithm is a process we follow to get to a solution. But in many ways, they're intimately related, and perhaps you could say that every algorithm has an underlying model that it relies on. And so then I said lastly, we get to our standard algorithm. So we had our concrete to the more abstract with the place value chart. And so then from the place value chart, we move to the standard algorithm because we no longer have this reminder of why we're physically circling and rebundling, or why we move those 10 ones over a column to the hundreds, right? It's a matter of remembering. We have, anytime we do addition, we have our units, we have our tens, and these are our rebundled. Because 5 plus 7 does not equal 2, right? It equals 12. And that was our place value chart where we had the 12 there. But instead, we write it up top for sake of kind of simplicity or tracking. And so it's important that we keep in mind that we may want to go immediately to the standard algorithm. We're like, oh, it's easy. We just want to get them to the standard algorithm. But the standard algorithm has the most hidden assumptions about why it works. It's very important that we start with set models, just putting things together and talking about the union of groups before we move on to base 10 pieces and rebundling, physically trading ones for a long or longs for a flat. And so here's an example. It says, examine and discuss the student's work. Compare the work of students 1, 2, and 3. And so what we have here, each case they're doing 27 plus 38. And in every case, they get the answer 65, which turns out is the correct answer for that addition. But instead what it wants us to really look at is the work the students are using when they found this. So in every case, notice that they wrote the numbers 27 and 38 with base 10 pieces, with longs and units. So up here we have 27, 2 longs and 7 ones, and 38, 3 longs and 8 ones. And so what they do is they do the actual act of regrouping. So we have 1, 2, 3, 4, 5. Notice that they've kind of clustered it into 5 and 2 and 5 and 3. Same down here and same over here. And so you can see how that 5 frame that you may have introduced in number begins to inform student work later on. And so here they are like, well, 7 and 3 more make 10. So I can circle and rebundle that as a long. And then I have 5 left over. That's my 5 units. And then I have 3, 4, 5, 6 longs, 65. And now contrast that with student 2. So student 1 did 7, counted on 8, 9, 10. And they said, you know what? I know that that's 5, and I know that that's 5. And so together that's a 10. And they put it at the bottom, because it doesn't inherently matter where you put the 1 when you rebundle. And then there were 5 left over. So we have 5, and then we have 6. And then the student here on the right, or in student 3, does essentially counting on. So they're counting on, they're like, well, we have 10, 20, 30, 40, 50, 55, 57, 58, 59, 60, 61, 62, 63, 64, 65. So there's counting on. And this is we haven't learned these yet, but they're tens facts. 7 and 3, whereas the second student didn't worry about the fact that these 7 were clustered in the original. They were like, oh, I have a set. I can look at all of these together. And if I do that, well, I'm just going to take those 10 because I already know that there are 10 there. And so when it comes to addition, there are lots of these models and lots of ways to show, and they're going to show up in lots of interesting ways in student work. But it's useful to classify types of addition problems. So these come from something called cognitively guided instruction, which was at the time a really radical idea that it's important that we understand teaching and learning from the perspective of the child, right? It's important that we understand how a child is thinking so that we can help them learn. And so there are 3 types of addition problems, and they're roughly in order of difficulty. So the first type of problem that a child can start to grapple with is a join result unknown. And so join just means add, because when we get to subtraction in the next video, we're going to talk about separate. And then result unknown, because we don't know how many we have altogether. So it says Connie has 35 marbles. Juan gave her 18 more. How many marbles does Connie have altogether? And now contrast that with a join, but not result unknown, but change unknown. She has 35 marbles. How many more marbles does she need to have 53 altogether? So now my result isn't what's unknown, but it's this middle piece that's unknown. And lastly, join start unknown. Connie had some marbles. Juan gave her 18 more marbles. Now she has 53. How many marbles did Connie have to start with? So, start unknown. We don't know how many she started with. But it turns out, for children and even adults, it's easiest to think about join result unknown. And so often you'll abbreviate that JRU, join change unknown, and join start unknown. And these get harder as we move from one to the next, because conceptually, it's easier when you think I have one set and another set, how many together? And then it's like I had some, and now I have this many. How many did I add? But when I'm like, I got some more and I have a whole amount, what did I start with? Tends to be the most difficult because we think back. And once we have subtraction, we start to use the fact that addition and subtraction are inverses, and we just translate the addition to subtraction, and that makes our life a little bit easier. And we'll talk about that in the next video. And so, like I said, the standard algorithm isn't necessarily useful when you have something as simple as 1 plus 4, right? Because you're going to either need to use a set model, you're going to need to count on, or use some other related fact. And so learning addition facts isn't the only goal of addition, but it is certainly one of them. And so I like to share this table with you, which comes from Bridges, which is a particularly well done elementary school curriculum. Goes PK through 5. And it breaks down all of our addition facts up through 10 plus 10 into a number of types. We have our add zeros facts in red, which is when you add 0 to a number, it doesn't change. Our count on facts, when we are with just looking at like, we need to start with some number and count on, say 3 plus 6. So we have 3, 4, 5, 6, 7, 8, 9. Our doubles facts, which are down the diagonal. And so knowing just immediately that 9 plus 9 is 18, because it's a double. And then once you know your doubles facts, you can do your doubles facts plus or minus 1, which just gives you those off diagonals. Make tens facts, and so I talked a little bit earlier about how we're going to want to be able to make 10 quickly, so knowing that 7 plus 3 is 10, 6 plus 4 is 10, and so on. Add tens facts relies on place value. Your add nines facts are just add tens, take away 1. Right, so we add 10 and then we just have to, it's like, so if I'm doing 4 plus 9, well, that's like 4 plus 10, which is 14, but I had 1 less, so it's 13. And then there are just some leftovers. We have, say, 7 plus 4 equals 11. And you know what? I would say 7 plus 4 equals 11, you could even start to think about as your make tens facts plus 1. And so that'll account for at least 2 of them. But then so much we don't quite get the rest, and so they're called leftover facts. And so that takes what really is 11 times 11, 121 unique addition facts, and breaks it down into, well, whenever you add 0, it doesn't change. You can count on for a lot, but you can also memorize your doubles. And once you have your doubles, you can add or subtract 1. There are only a handful of ways we can make 10. We can add 10 using place value. And then once we can add 10 using place value, we can use our add 9s. And then there are really only just a couple more. And so you may not have seen an addition fact table before. And I'm going to share, as we move through the rest, I'm going to give you a subtraction table and a multiplication table. And I'm trying to remember if there's a division table. Maybe not. We'll see. That'll be a surprise when we get to it. Okay. So up till this point has really been like the conceptual way of thinking about addition. There are lots of models, there are lots of algorithms and approaches we can take to solving them. But our textbook, Bilstein, Boschman, Libeskind, and Lott, have what's this really formal discussion of addition. And this formal discussion really heavily draws on our sections on sets. And so I think it's worthwhile to introduce that just so that you can start to think about addition in a perhaps more abstract way. So let A and B be two disjoint sets. And remember I said that means they don't have anything in common. So A has the elements A, B, C, and D. And B has elements E, F, and G in it. And so if the cardinality or size of A and the cardinality of B is B, then A plus B is the size of their union. So to make that concrete, the size of A is 4 and the size of B is 3. And so we have the size, then A plus B, or 4 plus 3, is the size of A union B, which is 7. And that's what's in this picture right here. 1, 2, 3, 4, 5, 6, 7. Now you would never introduce it in this way to a child. But why we're doing this is to really think, okay, so we have a certain understanding of addition, and then the mathematicians have an understanding of addition. And we want to bring those two things closer together in our minds as future teachers. And so whole numbers, and so this is something I haven't emphasized up till this point. When we talk about addition, subtraction, multiplication, and division, the next couple videos, we're only going to be talking about whole numbers. We don't have fractions yet. We don't have decimals, non-terminating decimals yet. We don't have negative numbers yet. We don't have numbers like pi or anything like that. So when we're talking about whole numbers only, 0, 1, 2, 3, and so on, right? Maybe we could also call those the natural numbers. We have things called closure, commutativity, associativity, and identity. Closure means two numbers, two whole numbers, add to another whole number. So if you have two numbers that aren't fractions, you're not just going to magically have a fraction on the other side. Commutativity, that's that notion of the number line that 5 plus 3 is the same as 3 plus 5. Because those lengths, regardless of what order you put them in, will always end at 8. Associativity means you can add, if you have 2 plus 3 plus 4, well, that's the same as 2 plus 3 plus 4, or 2 plus 3 plus 4. Let me move my face over here. Oh, I'll just put it on the bottom. See my eyes. Which is 5 plus 4, or 9, or 2 plus 7, which is 9. So associativity means we can group numbers together and add however we like. And then identity just means add 0 doesn't change. And each of these has their own slide, but I wanted to give you kind of the informal big idea before we dig into them in detail. So a formal statement of the closure property. If a and b are whole numbers, then a plus b is a unique whole number. So if a and b are whole numbers, you can add them together, you'll get a whole number, and you'll only get 1. So 3 plus 5 equals 8, and it only equals 8. 3 plus 5 doesn't sometimes equal 9 or sometimes equal 7. It always equals 8. So for example, 5 plus 2 is a unique whole number, 7. So this tells us that the sum of two whole numbers exists. So you can take two numbers and get something out, and that it will only give you one thing on the other side. The commutative property, if a and b are whole numbers, then a plus b is the same as b plus a. And so this picture on the left shows you the number line that I drew on the previous slide. But also here we can see it with two rods, one of length 5 and 3, and doesn't matter which one comes first, the same overall length from here to here is 8. So this means add in any order. Associative property. This is where I said you could cluster in any way. If a plus b plus c, we can either do a plus b first or b plus c. What was my example? 3 plus 4 plus 5. I don't think that was an end, but we'll do it anyhow. 3 plus 4 plus 5. I think it was 2, 3, 4. Yeah. So 3 plus 4, or 4 plus 5. 3 plus 4 is 7 plus 5 equals 3 plus 9. And 7 and 5 is 12. And 3 plus 9 is 12. And so we can add the groups in any way and still get the same result on the other side. Identity. So the fact that we have an additive identity is a special property. So 0 is that number. You can add 0 to any number and get that number back. So a plus 0 equals a, and 0 plus a equals a. And so that was that top row and that first column of our addition facts. And this 0 is called the additive identity. So some examples. Which properties of whole numbers are illustrated in each of the following statements? 6 plus 8 equals 8 plus 6. Remember, that is commutative property. You can switch places. Thinking about like commuting to work, going from place to place. If we have 1001 plus 834 is a unique whole number, that's closure. Two whole numbers add together to give you a whole number, and it will only give you 1. 3 plus 6 plus 9, and here the 6 and the 3 switch places. That's commutative. And then here we have 8 plus 5 plus 2 equals 2 plus 8 plus 5. So from there to there was commutative. And then instead of having 8 plus 5, we switched to 2 plus 8. And so from here to here is associative. And so it's important that when we look at these, we can see what is happening. Why can we make these changes without changing the result? And it's because we have commutativity, closure, and associativity of addition. And so here you have those typed more neatly. And so I also want to give you a formal definition for less than, because informally we can say, well, if I have a number line and 0 is here and some a is here and b is here, a is less than b if it's left of b on the number line. and we write that a less than b. But our formal definition is that a is less than b if and only if there is some natural number k such that a plus k equals b. And think of it this way. If a is less than b, then a plus some amount, it's going to be a whole number, will give us b. And we're just going to call that amount k. So a less than b means a less than b, or a. So I just gave definition of less than, but that's a or less than or equal to. So it means that a is less than b or a equals b, and a is greater than b is the same as a is less than b. So it's giving the idea that if a is less than b, it means that you can add something to it to get to b. Okay. I'm going to give you some mental math strategies and some estimation techniques, and that's where we're going to end this video. So for mental math, we can add from the left. So if we have 76 plus 25, and that was that one where we had our place value partial sums, we had the 10, 70 plus 20 is 90, and 6 and 5 is 11, 90 plus 11 is 101. And so this is mainly, I want to introduce these to you so that you can pick ones that work well for you. I'm not going to say, add these 7 different ways, or add this way and this way. I may ask you to use like a partial sums or something like that, but I'm not going to be like, what are the 10 mental math strategies? There aren't 10 mental math strategies, but what are the 4 mental math strategies? Find it using each of those ways. Breaking up and bridging. 76 plus 25. Well, I can just do, if I split this bottom number into 20 plus 5, I can say 76 plus 20 is 96, plus 5 more is 101. And so we add that first number to the tens of the second, and then we add the rest. Trading off, if we have 76 plus 25, you can take 76, you can take 4 from, so we take 4 from the 25, and then we give 4 here. So 76 plus 4 equals 80. And then after we took 4 away, we were left with 21. So 80 plus 21 is 101. So we can add from the left. So that's using place value. We can break up and bridge, which honestly isn't terribly different. But notice what's happening here. And so that's why I say not terribly different. They are different because here we did 70 plus 20 and 6 plus 5. Here we did 76 plus 20 and then 96 plus 5, right? And so there is a difference between these two. Trading off, 76 plus 25. This is where we're using the fact that we can compose and decompose. And more specifically, this goes back to our number line model. 76 plus 25 is the same as 80, and has to end at the same spot, 21. Because it doesn't matter if I split it here or split it here. My full length on the number line is unchanged using compatible numbers, and so often this is when you're working with a string of numbers. You can see that the 130 and the 70 give you 200, the 250s give you 100, so you have 320. You can also make compatible numbers. You're like, well, I know that 25 and 75 give me 100, and so 76 is just 75 plus 1. And so you're like, well, that gives me 100, but then we took that 1 unit kind of away here, and so we have to add it back on, right? And so breaking it up that way. And so see how these strategies, in many ways, connect to our models, either number line or our addition facts or our make tens facts or our place value way of addition, right? So all of these mental strategies connect back to those kinds of ways. And for different students, different strategies will be easier and harder. And so our goal is not to say every child needs to know every single one of these strategies, but say, children, here are a bunch of strategies. You tell me which one makes sense to you and use it. And so some addition. And I'm not going to spend as much time on addition. So front end with adjustment just says add the fronts. So if we want to estimate this, we can have 4, 5 is 9, 10, 11. So we have about 1100. And then they're like, well, this and this is about 50, and that's about 70. So that's about 120. And so our total is about 11 or 1220. Right, and so that's what adjusted means, is you use your largest place value and you kind of round some others and go from there. It's important that we teach estimation because estimation lets us check. So estimation helps us check if our answer makes sense. And remember, in our 6-step problem solving process, the last one was looking back and making sure that it makes sense in the problem. This is worthwhile because suppose I did this and I say it should be about 1220. But when I was adding, I went 474 plus 522 plus 231. And I was just like 4, 5, 6, 7, 7, 8, 9, 10, 11, 12, 2. And then I was like 4, 9, 11. Like, man, I'm off by over 100. Am I sure that's right? And then I'm like 7, 8, 9, 10, 11, 12, 2. Oh, I forgot to carry a 1, right? And so it helps me to see when I've made a mistake. You don't always have to or estimate so precisely. You can look and you're like, well, 39 and 64 are about 100, and 20 and 30 and 50 are about 100. So it should be about 200. And I think you'll find that you're not too far off. 9, 10, 11, 12, 13, 14, 18, 27, 2, 4, 7, 10, 16, 20. Not too bad. So clustering is useful when you have a bunch of numbers that are around a similar number. So look here, we have 4,724, 5,262, 5,206, 4,992, 5,331. They're all about 5,000. So we have 1, 2, 3, 4, 5 times 5,000. So it's about 25,000. And you could add them and see what it actually turns out to be. Let's see if we can do that relatively quickly. This is one of those instances where trying to use photomath did not work to my advantage. Let's edit that input. So we have 4724 plus 5262 plus 5206 plus 492 4,724 plus 5,262 plus 5,206 plus 4,992 plus 5,331 is, and it is 25,515. So we were off by about 500, but if we're talking about 25,000, that's not so far off. Oh, and so there's the next step behind my writing. Rounding, that's probably the most direct. 7,000 is about 7,262, about 7,000. 3,806, about 4,000. It's going to be about 11,000. And since this one ended up the second number, we round up 194, and here we round down 262. This is going to be slightly under. So let's see if 7262 plus 3806 is 11,068. 11,068 is slightly more than that. Perfect. And then lastly, you can use the range. Fewer problem, 7,262 plus 3,806. You can get a lower estimate by rounding both down. Round down. So 7,262 rounds down to 7,000. This one rounds up to 3,000. So we know it's going to be at least 10,000. And an overestimate, so round up. So this is our underestimate. This is our overestimate. 7,262 rounds up to 8,000. 3,806 up to 4,000. So less than 12,000. And this is the same problem we had on the previous slide. So 11,068 is within that range. So I know that is a lot of information, right? Like I introduced like 8 or so different models and algorithms for working with addition. I introduced the CGI terms for join result unknown, join change unknown, and join start unknown. I introduced a formal discussion, so thinking about sets, closure, associativity, commutativity. I introduced ways for doing mental addition and ways for doing estimation. But again, this is all an attempt to start to think about addition, not so much as while we're learning about the content of math, this is really what do we need to know about the math that will enable us to be better teachers in the future. And so I hope this was an enjoyable discussion of addition, and I'll see you for subtraction next time. Bye, everyone.